you can see a sketch here of the various set of models, candidates, and so on. The most, let's say, famous is the WIMPs model, so weakly interactive massive particle. So the candidate is just adding a new particle to the standard model with mass between 10 giga electron volt and a few TeV. With cross-section approximately of the weak scale. With these parameters, the relic density of the WIMP particle has naturally at least the right order of magnitude that is expected from cosmological observation. So this is the so-called WIMP miracle. Basically, this was the main motivation to a huge and experimental effort that has been done during the last 20 years to try to detect them. Among these experimental groups, there is the Xenon collaboration that is composed by 28 institutions worldwide with more than 170 scientists. You can see here that the people from our collaboration comes from all the region of the world, and you can see one of the last collaboration meeting that, of course, was done in a virtual way because of the pandemic. And the main goal of this collaboration is the detection of a dark matter particle with liquid xenon TPC. So what is TPC? TPC stands for the time projection chamber, and it is basically a cylinder tank filled up to a certain level with liquid xenon in this case, and on the top of that there is a thin stratus of gas xenon. The cylinder is instrumented with two arrays of photomultiplier tubes, one on the top and one on the bottom of the cylinder, to detect light. Also, through a set of electrodes, there is a drift field on the whole volume of the TPC that it's meant to drift electron through the interface between liquid and gas xenon. So how does it work? When a particle hits one of the electrons of the nucleus of the xenon atom, it releases some energy via recoil, electron recoil or neutron recoil, nucleus recoil, sorry, and produce a prompt scintillation light that is what we call S1, which is and releases some electrons. These electrons are drifted up through by means of this electric field. They are drifted up through the interface between liquid and gas xenon, where they are extracted with another electric field much stronger. And then when they hit the gas phase, they produce a secondary light signal that we call S2. And from the time between the two signals, we can infer the z coordinates of the primary interaction, and from the pattern of the S2 on the top array, we can determine the x and y position. So this gives us a very precise 3D event reconstruction of the position. And also, exploiting the two signals, S1 and S2, we can compute the energy of the event. And also, given that we have this very precise 3D position reconstruction, we can visualize the detector in a very precise way. And also, we can do event discrimination, so discriminate between electron recoil and nuclear recoil using the ratio between the S2 and S1 signal. The last or at least for now, iteration of this technique is the Xenon 1-ton experiment that is located at Laboratorio Nazionale del Gran Sasso here in Italy. You can see a picture of the water tank of the experiment and the facility where all the subsystems are stored, like the AQ, cryogenic purification, Xenon storage, and distillation columns. The Xenon 1-ton exploit cylindrical TPC of 1 meter diameter and 1 meter height around. We're using a mass of 3.2 tons of liquid xenon and an active target of 2 tons. The drift field is 100 volt per centimeter, and we took data for 278 days. The X and Y reconstruction is done via a neural network algorithm to get a position resolution of around 1-2 centimeter. And also we have a very good energy resolution, which is the best actually in liquid xenon TPC of 1.6% at energy of around 2 MeV and 6 at energy of 40 kiloelectron volt. We took data for the largest exposure reported so far with this kind of detector. And also, the electron background rate is 82 events per ton per year per kiloelectron volt, and is the lowest electron recoil background ever achieved in a dark matter detector. This was indeed a fruitful experiment. Here is a list of the publications that derived from this all less than 300 days of operation of the Xenon experiment between 2017 and 2018. And I highlight some of the most important results here that I'm going to describe a little bit in this talk. From the first dark matter results to the last and search of and the last and most famous excess in electronic recoil from Xenon 1-ton data. First of all, let's stick to the main argument, that is dark matter search. So no WIMPs showed up so far, so we can set a limit. And you can see here all the events candidate as a WIMP event. The results has been done on an unbidded profile likelihood using the corrected S1 and S2 radial and Z position. The pie chart on this event by event show the relative PDF to the best fit with 200 gigaelectron volt WIMPs mass with a cross section of 4.4 times to the minus 47. You can see that we couldn't identify any WIMP event, so we set a limit that is 7 times more than the previous limit set by similar experiment. So this is actually the most stringent upper limit on WIMP nucleon cross-section on the worldwide base. So the minimum of the curve is at 30 gigaelectron volt centimeter C square, and it's 4.1 times 10 to the minus 47 centimeter square on the cross-section. We can extend our search to lower mass dark matter candidate. So you see the previous results was this blue line here. We could extend using the ionization only channel, so only S2, and the Migdal effect. We could put constraint on the WIMP nucleon cross section for dark matter particle of mass below 10 gigaelectron volt. And in this case, we mitigate the background with a strong event selection rather than requiring a scintillation signal, the S1 signal. Here we have also world-leading constraint on Wim-Lumpen cross-section for these ranges. But Xenon and Argon started, let's say, the exploitation of this technique for multi-purpose, not only dark matter, but also other interesting topic like double electron capture in 124 xenon nucleus. So what is double electron capture? It's when two proton converts into neutron, absorbing two electrons from the atomic shell, mainly the K shell, and emitting two electron neutrinos. Then the filling of the vacancies results in a detectable cascade of X-ray and OJ electron with a Q value of 64.3 kiloelectron volt. So you see here the spectrum where all the background are reported, and the black Gaussian peak is the signal expected from two neutrinos double electron capture. The most important background is coming from iodine 125 that is induced in our detector from calibration with neutron. So we needed to take a good care of this kind of background. We were able to measure actually the lifetime, that is 1.8 10 to the 22 years. That is the longest half-life ever observed. And it was a very high significance, 4.4 sigma. And it was published in Nature because of this importance of these results. And also it gives an important output for nuclear structure models. Then coming to the most juicy, let's say, results from Xenon and Argon, the famous low ER excess. So looking for electron recoil below 30 kiloelectron volt, we got 284 events observed, whereas only 232 were expected. You can see here on the plot that the red line is the expected background, and you can see the clear excess here from the data. This is correspond to 3.3 sigma fluctuation of the background. This could be explained by a leakage of Argon 37 with a rate of 65 events per ton per year. But from air measurement in the detector, the leak rate is constrained to be less than 5 events per ton per year. So this cannot be, so the hypothesis of a leakage of Argon 37 is excluded. So what is this? What is this effect? Several hypotheses were made. It could be caused from solar action with, again, around 3 sigma significance. Neutrino magnetic moment, enhanced neutrino magnetic moment, bosonic dark matter, Exxon-like particle, dark photon, many hypotheses were made. Also, it could be explained by beta decays of tritium, and with a 3.2 sigma significance and corresponding to a relative concentration of tritium in xenon of 6.2 10 to the minus 25 mol over mol. So you see here, if we confront the two hypotheses, the tritium-only and tritium plus axion hypothesis, we have that the sensitivity is reduced from 3.4 sigma to 2. Actually, this hypothesis cannot be neither confirmed or excluded because with our current knowledge of the production and reduction mechanism of the tritium inside the detector. So for now, the mystery remains unsolved, but only up for now, because Xenon and Argon is only one step of the long history of xenon-based dark matter detector. His predecessor, Xenon 10 and Xenon 100, had also very compelling results, but the present, no more future, the present is the Xenon and Argon detector that is now under commissioning at the LNGS, and I'm going to talk about this. I will also mention Darwin detector that is a proposal for the future. The Xenon and Argon, so the present or near future, better to say, of this field. So when Xenon and Argon was built, all the subsystem infrastructure were thinked to have a fast update for a larger TPC detector. In fact, we have a new TPC that contains 5.9 tons of liquid xenon, and it is instrumented with almost 500 photomultiplier tubes that you can see here. This is a real picture of the TPC. And this is, on the other way, this is a sketch of the new neutron veto, that is this panel around the TPC, instrumented with photomultiplier tubes and immersed in gadolinium-doped water. There is the new liquid purification system that aims to have an electron lifetime of greater than 7 milliseconds, the new radon distillation column that you can see here, and the radon-free purification pump that you can see here. And also there was a very detailed campaign of material selection and cleaning. This is the expected sensitivity for the Xenon and Argon experiment. And if we assume 4 tons of fluid volume and an exposure of 20 tons per year, we could reach 1.4 10 to the minus 48 centimeter square at 50 giga electron volt. And of course, now that we have this low ER excess, this is one of the things that we want to address as soon as possible. So what is the situation now? So latest news from LNGS, let's say. We had a little bit of delay due to the pandemic, but we are still in a good shape. So we finished the installation on summer 2020. You can see here a picture of the installation of the photomultiplier tubes and the assembly of the TPC. Then it was moved to the underground lab. This was just a few days before the lockdown in Italy. And after that, we installed the detector in the underground laboratory. There was the installation of the neutron veto. You can see here a very nice picture of these panels armed with phototube around the cryostat and the heroic people that did this job during COVID time. And currently, we are testing all the subsystem and taking commissioning data. And we aim to have the first science data before the end of the year. Just a few words about Darwin, that is going to be the further update of this program. And it will exploit 40 tons of liquid xenon with a very big temperature chamber, and has a goal of having an ultra low background. And this is a sketch of the timeline that I think this will be delayed because of COVID situation. There is Darwin will be a multi-purpose detector. And this is because it could reach, this is the projected sensitivity, and you can see it can reach the famous neutrino flood. It is the irreducible background given by neutrino nuclear scattering from solar neutrinos. But this indeed could be an obstacle for dark matter search, but can give us the opportunity to measure the solar neutrino flux. So in principle, we could be able to have precise measurements of the pp and beryllium-7 fluxes with precision of around 1%. And we can also detect supernova neutrinos and many others interesting physical problems. So this is my summary. I think I'm at the end of my time. So xenon-based dual-phase temperature exchange chamber has proven to be the leading technology in the field of dark matter direct search. Xenon made a considerable improvement to the field and through the years, both in dark matter and neutrino physics and technical design for low background experiment. Xenon is about to start its physics programs and aims to improve the results of its predecessor and answer, first of all, the low ER access question. So fresh new data from Xenon and Ton are on their way, so stay tuned. And thank you.
Thank you, Ricardo, for the interesting talk. We have time for a couple of questions, and actually we have some written question in the chat. One of them is, what is the technical or experimental lowest threshold of measuring dark matter nucleon scattering, cross-section 10 to minus 15 centimeters square in near future? This is one of the questions. I think maybe you answered to this at the final slides.
Yes, I think this is this plot can answer to the question.
Yes, this is the okay. Do you want to add something more about this?
Can you repeat the question?
The question is, what is the threshold? The threshold of this 10 to minus 15 centimeters square, the technical threshold.
That means that the minimum, the threshold you can reach, you cannot reach. I suppose this cross-section is very small. So as far as I can see your plot, is a neutrino flow is almost reached around 50 GeV, 10 to the minus 50 centimeters square. So are you expect to probe even smaller cross-section, permit by technical and all the measurement?
Yes, okay, this depends on how much we will be able to lower our radioactive background from the using in Darwin. We are studying many other aspects, of course, because the main background, for example, comes from the, in Xenon, one of the main background comes from the PMT. So we are aimed to use another kind of detector, for example, to have a more radiation-free situation. So it is not merely a question about the threshold, but could be.
Can you go beyond the 10 minus 50 centimeters square?
With Darwin, I don't think so.
Even in 10 years, do you expect you just give me roughly? I'm not going to precise the technique.
Okay.
Just what you feel.
I can only say from the sensitivity study that exploiting Darwin at its maximum, I think this is running for. Let me check, but I think that this sensitivity is computed with. I wrote somewhere the exposure expect. Okay, yes, it's 200 ton per year. So it should be with okay, should run for 5 years. Okay.
Okay, thank you. Thank you for your question.
I should run the full Darwin experiment for 6 years.
Thank you for your answer.
Yes, there is another question. Why the data points in the Xenon 1T electron recoil plot at 17 keV and the excess between 15 to 30 keV are not considered anomalous? This is the point. Yes, you can see there is some data point between 15 to 20. Yasaman asked why you did not consider this as an anomalous, just you consider this at the first part as a anomaly. This excess.
Okay, yeah. Okay, you mean okay? This point here, I think you mean.
Yes.
Okay. I think that they evaluated this the significance and of this only this point, and it was not that significant as this one.
How about the points between 25 and 30 keV?
Sorry, can hear very, very bad. Sorry. I cannot. Did you say something?
There are some data points. Oh.
I think her question is about 15 all the way to 30 because you can see some inconsistency between the red line and the data point.
Ah, okay, I see. Okay, I see. Okay, this probably is not that significant. I didn't make the calculation of this analysis, but I think the only significant axis is this one.
So let's thank a speaker again. I think since we have no time, we are going to the next speaker. Gili, can you please share your screen? Okay, thank you.
Yeah,
please go ahead.
Okay, yeah, thanks for giving me the opportunity to tell you about some recent and less than recent work with my collaborators, Jeff Dole, Robert McGehee, and Tintin Yu. I'm going to apologize in advance. I've been having some connectivity issues today. If my connection drops out, I'll need some 30 seconds to reconnect, so please bear with me if that happens. And of course, I'm actually having problems scrolling through slides now. Okay, very good. Okay, yeah, so as Ricardo gave us a very nice introduction to direct detection and a general overview of the status of dark matter. So with that in mind, I'm going to tell you about a new class of signals at direct detection experiments. So that is the subject of today's talk. Actually, Soroush, would you mind turning your video on? This is how I'll know if I got disconnected so that I'm not talking to myself. Thank you. Okay, yeah, so just to, again, Ricardo reviewed this, but I'll review again kind of from a more model building perspective, the effort to search for WIMP dark matter, right? So the vanilla WIMP paradigm is we have a dark matter particle, it interacts via the weak force with nucleons, right? It's got a mass of 10 to 100 GeV, or 10 GeV to 10 TeV, and it's stable, right? And again, as Ricardo was just telling us, we can search for these WIMPs in direct detection experiments by just waiting for them to come and scatter off of the target material. And in this case, the recoil energy that's measured, right, is proportional to the velocity of the dark matter. Okay, but of course we haven't found WIMP dark matter yet. This is kind of a much older version of the plots that Ricardo was showing, but it's kind of nice because it also has some SUSY models that are now excluded. But the punchline, right, is that we haven't seen dark matter. We're pushing up, we haven't seen WIMP dark matter. We're pushing up against the neutrino floor. And you could say, what kind of models live in this space here that's below the detectable thresholds for nuclear recoils, right? So in order to build models in this for this regime, right, you actually kind of give up the vanilla WIMP paradigm. You say you're no longer necessarily interacting with the weak force and you're going to much, much lighter dark matter. And the way this helps you, right, is if you imagine dark matter scattering off electrons, right, the recoil energy, right, is inversely proportional to the mass of the target material. And so you can access much lower recoil energy than in this case. Right, the parameter space is quite constrained, coming from CMB and other bounds. Nevertheless, there's a lot of searches for this, which can arise right from a higher dimensional operator of this form. But what I want to tell you about today is what if you also give up stability? If you give up stability, you can have these new class of signals that we pointed out, where the dark matter is actually getting absorbed by the target. Okay, so what do I mean by that? You can have kind of different classes of operators. You can have scattering off of electrons, scattering off of or nucleons. And in each case, because the dark matter is being absorbed, it's an inelastic process, and the dark matter comes in and it actually emits a standard model particle in its place. And what happens kinematically is that you actually absorb the entire rest mass of the dark matter, right? So this dominates all your kinematics and all your signals, opposed to having like a velocity dependent a signal like you do for the case of normal elastic scattering. So just by kind of kinematics alone, this gives you a lot of distinctive new signals. And you can repurpose not just xenon experiments, but a whole host of dark matter direct detection experiments and neutrino experiments to look for these new signals. They'll also have very distinctive shapes, so there generally won't be a neutrino floor, or it won't be the same kind of neutrino floor that Ricardo was showing you earlier. Okay, so where do we imagine these models coming from? I'm just going to generically write them down as some higher dimensional operator. So these gammas are some Lorentz matrices. The point is the dark matter interacts with a standard model particle, and it can scatter off protons and electrons. Right, in this particular case, it's emitting a neutrino, and then this scale of the new physics is going to be constrained by a whole host of other experiments. Now, of course, the elephant in the room right now is that we've given up stability. This operator, of course, allows the dark matter to decay through various different processes, right? So for instance, you can imagine decaying through a loop of these protons or neutrons into electrons, right? So you want to ensure that these rates are relatively small. And this is going to be a very model dependent question, which diagrams actually contribute and what the rates are, but they're generically going to scale as the dark matter mass to some power. So really what that tells you is that this is going to be a very good way to probe light dark matter. So kind of in the back of your head, this is going to be like searches for 100 MeV or less scale dark matter. And then, of course, we have constraints coming from colliders and other experiments on this mediator scale, and we generally want it to be heavier than a TeV. Again, that's a model-dependent question, but this is kind of the parameter space that we're going to be able to probe with this new class of signals. Okay, yeah, so now I really just want to focus on the signals that you can have at a whole host of different experiments. And I want to go through kind of the three different kind of operators that you can have. So let me start first with neutral currents signals where you have nuclear targets. So you can see these papers for more details, but the idea is you have this higher dimensional operator and it allows the dark matter to scatter off some nucleus, could be xenon or some other target material, and the nucleus absorbs the entire rest mass of the dark matter and emits off a neutrino, right? So the kinematics for this are the neutrino is going to be pretty energetic. It's going to basically have the entire mass of the dark matter at its disposal. And then the recoil energy, you can just compute from kinematics. It's not going to be huge, but the point is it's independent of velocity. It just depends on the dark matter mass and the mass of the nucleon, right? So these are two kind of now parallel signals you can search for, is this high energy, this emission of this high energy particle and this recoil energy. In the case of the nuclear scattering, right, you're probably not going to look for this missing energy. You're really going to focus on measuring the recoil energy. So unlike the case of normal elastic scattering, in this case, because of the kinematics, you're going to have all the events in one bin. And different isotopes of the target material will actually correspond to different bins, and you'll be able to see that. Again, there's no neutrino floor, and you're sensitive to light dark matter. So let me actually give you an example of what that looks like. This particular case, I'm considering scattering in CREST, right, which has this calcium tungsten crystal target material. This plot is the rate in counts per day versus the recoil energy. So this black line is the kind of normal elastic scattering WIMP cross section that you would expect for a 7 GeV WIMP. And what these red lines are the signals from the absorption, right, corresponding to these different target materials within this molecule. And furthermore, if we zoom in on this peak, this tungsten peak right here, you can actually see the different isotopes of tungsten in here, okay? And yeah, so the point is this is an incredibly different kind of signal from the normal case of elastic scattering. Okay, so we can use this to actually calculate the rate, and then given a exposure at a current experiment, we can project limits that this experiment would see if they were able to do this search. So for instance, this is plotted as limits on this basically dark matter nucleon scattering cross-section. It's parameterized basically in this way in terms of the mass and the scale of the operator versus the dark matter mass for this given operator. This is the line such that given the current exposure, CREST would not have seen 10 events. So this looks very different from kind of a normal continuous elastic scattering line. And in particular, right, these jagged edges correspond to the different isotope peaks, basically when the different recoil energies come above and below the experimental threshold. So this is where that shape comes from. Now, again, back to kind of the elephant in the room, you have to ask what the decays are and do they constrain your parameter space. So, and I forgot to say this gray region is excluded because you want the scale of the operator to be heavier than a TV. So yeah, so in this particular case for the decays, there's a lot going on if you consider the UV models contributing to this. And these lines just show places where you would fine tune the contributions for the decay by some other UV model, UV physics, okay? So the point is, from a kind of theoretical perspective, this is slightly less appealing. But nevertheless, you can still search for these kind of signals at various different experiments. You'll see that like Xenon, which is a neutrino experiment, is here too, in addition to various different xenon experiments, argon experiments. Again, there's CREST, all kinds of other experiments. And again, because of the kinematics, we really win with large volume experiments, right? So Xenon can really probe down to very much smaller cross sections. Okay. Now, if we do want to consider more theoretically appealing models, we would need to go to even lighter dark matter searches, right? Because again, this decay rate is going to scale as the dark matter mass to some power. So there's no experiments really looking for very light dark matter in this context, but there are some proposals, and basically what this curves show is if you had some kind of hypothetical hydrogen or lithium experiment with some hypothetical exposure, this is the kind of projected limits you could expect, and you could really probe all the way down to the dorsoroidal limit of the dark matter without having to do any kind of tuning in your UV model. Okay. But perhaps a more appealing way to probe for even lighter dark matter is to actually consider scattering off of electron targets. Okay, so it's the same operator as before, but now I'm considering, instead of a nucleon, I'm considering this coupling to 2 electrons. Again, this is the UV scale. And again, just because of kinematics, you can go to lighter masses because the target mass here is now the electron mass. Okay, however, now you're considering scattering off of bound electrons, and there's quite a bit of subtlety to how to do this computation. In particular, you have to compute form factors to account for these scatterings. So because it's a little bit more complicated, let me just focus on xenon for this part of the talk and tell you how a search there would work. So in particular, what you look for in xenon, right, is this dark matter coming in. It gets absorbed by one of the electrons in various different possible shells of xenon. It emits a neutrino, and the signal for us will be the case where it also ionizes the electron, and the electron gets spewed off, and you can look for an ionization signal. So this would be a search you can do with the S2 data set in xenon, for instance. Yeah, in order to actually compute this, we need the form factors, right? So the rate for this ionization for a given recoil energy is going to have all these contributing parts to it. They're not so important. This is basically the amplitude, the energy transfer. And then, yeah, you have these contributions for the form factors that will really depend on the wave function for the different shells. Okay, so there's an example of them. for two different masses of dark matter, right? This is just the formula to compute them. These are the radial wave functions. Don't worry too much about the details of this expression. There's a lot of literature, for instance, this paper on how to compute these form factors. There's even a website where you can go and you can download the wave functions. The point is this is a computation we just needed to do for each of the different xenon shells, given some binding energies. And you get kind of the following results for different masses of dark matter, okay? All right, so you can do that. And once you have the form factors, you can do the same thing as before, and you can make these projections for what, given some number of events, for what these different xenon target material experiments would have expected to see. Now, again, this is kind of a model-dependent question. So here I have kind of two different possible models, a scalar operator and a vector operator. And these curves are, again, projections for the exclusions of searches for what you would see with 10 events. And in particular, this red curve here is the xenon excess that Ricardo was talking about again. So this is a chi-squared fit to our particular model for fermionic absorption, the best fit point that would explain the xenon excess. Okay, and again, these shaded out regions come for the model dependent constraints on various different decay modes. Please see our paper for more details or talk to me afterwards. Okay, let me get to the third class of signals, which are perceived through a charge current. In this case, I'm considering a dark matter coming in, getting absorbed by a nucleon, emitting an electron in this case, because it's a charge current, and then actually changing the number of protons in the nucleus itself, okay? So really what this process does is it sort of induces beta transitions, right? So normally, these target materials are very stable, but because this dark matter can impart its rest energy onto the target material, you can, as long as you're kind of have heavy enough dark matter, you can have beta type transitions, right? So either emitting an electron or a positron and changing the atomic number of the nucleus. And these signals are very rich because they actually have multiple correlated signals that can be searched for, and they really depend on kind of the different isotopes. So let me give you an example of that, right? So consider dark matter coming in and getting absorbed by a xenon 128, in this case, target in one of the xenon experiments. Right, the absorption process in this case, right, this is above the threshold for inducing beta minus decay. So what you get is a cesium nucleus and an electron that carries the rest mass of the dark matter. Now, this case, it's actually an excited state of cesium. The reason for this is there's various different angular momentum selection rules that are at play for these kind of transitions. So in order to obey them, really what's going to happen is if you start with the ground state of xenon, you're going to transition to some excited state of cesium, which is unstable and will very quickly decay. So you really have a lot of things going on here. You can search for the high energy electron or positron, right? Again, with, for instance, the S2 data set. You have the recoiling nucleus. You have a photon, right, from the de-excitation of this nucleus. And you have the decay of the unstable nucleus itself, right? The cesium isotope is unstable and it's going to decay with some lifetime, right? So, and you can really do this with all kinds of different experiments, right? With all kinds of different target material. So this yellow, I've highlighted the xenon to cesium transitions, but you can also do this in argon detectors, right? Like DarkSide or various other different detectors. And in particular, you could do this at Borg-Xeno, for instance, right? So these are all the different possibilities. And what you're going to get is for each one of these different transitions, you're going to get, or different isotopes, you're going to get a host of different allowed transitions that are allowed by your angular momentum selection rules, right? So this is kind of what this plot is showing, is that for a given atomic number and different target materials, there's going to be a different number of transitions for each isotope that are all going to contribute to the rate. And because you have all these different transitions, if you again calculate the rate for this and make projections, you'll have very distinctive shapes. So all of these jagged edges come from the various different transitions that you can have in this different, various different target materials. So yeah, here's the kind of the xenon ones, and there's Borg-Xeno, Super K. Yeah. Yeah, so that's kind of it. This is kind of the summary, is with these 3 different classes of operators, you really can search all the way from a KV up to a couple tens of MEVs. Above that, you could potentially do other searches to get to 100 MEV, but yeah, like that requires a little bit more theoretical work. But that's it. I'll end there. So thank you.
Thank you so much, Gili, for the very interesting talk. Okay, we have time for a couple of questions or comments. Is there any? Actually, I have 2 questions. Do you have any hint of the UV model of these effective operators in your consideration?
So we have some, in these papers, we have some proposed models, right? So they can come from like dark abelian gauge groups. But I guess by hint, do you mean, do we have models that can work, or do we have additional kind of experimental hints of these models?
No, because you have some scale and energy scale in your effective operators that shows at which scale this this new physics will appear. I mean, do you have any intuition or any sense about the scale that this physics will be important?
Yeah. So it depends on the model. So for instance, yeah, this is just a backup slide, right? So yeah, for the neutral current, you can have like a Z prime mediator, and likewise, there's left-right symmetric models for the charge current. And then really all you can say is, given these specific models, there's going to be bounds on the size of lambda, right? And all you can say is that you want lambda to be bigger than a TeV. We don't really have a way to predict any favorable scale of what lambda will be in this context. Maybe with like a very specific model, you can do a lot of model building and play around with it. But the point is all of these models, as long as lambda is like greater than a TeV, it roughly works. Does that answer?
Yes.
So you mean upper value of the lambda would be TeV, 10 TeV, 100 TeV? Can you more precisely?
It depends on the model. I mean, really, like, yeah, I would,
just upper magnitude, 10 TeV, 10 TeV, or 100 TeV. Just give intuition. What do you think? Because 1 TeV, 100 TeV is very different. So just
it really depends on the model, and we have, that's why we have we've used 1 TeV conservatively here. So this is what we're showing in this plot. Some of these plots are a little bit more specific. We're actually considering not just we're not just bounding lambda directly, but we're actually considering constraints on like chi getting produced, overclosing the universe and things like that. So this puts more direct constraints on lambda, and this is what gives us these exclusions. So it's a very model dependent question,
Okay, I have very short question also about this gray region. You mean this in this part you have overproduction of dark matter or something like this from cosmological?
In that particular model.
Yes. Okay. Okay. Good. Thank you so much. We can move to the next speaker. Actually, our next speaker is Yasaman, but I cannot see her. She was with us at the beginning, but now I cannot see her. Maybe we can a bit change and move to Victor if he has no problem. Then we can continue with Yasaman and hope she can join us afterward. Victor, can you please share your screen?
Okay. Okay. Do you see my screen?
Yes.
Yes.
Okay, I'll proceed. Okay. So I have several topics in my talk. One of them atomic ionization, but scalar dark matter and solar scalars. Scalar dark matter was studied before, but calculations was wrong by up to 8 orders of magnitude. So we just corrected this mistake and did proper calculations. So we did relativistic Hartree-Fock calculations and corrected several orders of magnitude error. People before used Born approximation, which does not work due to violation of orthogonality condition between bound and continuum electron wave function. We get new limits on electron scalar coupling from Xenon 1T data. Actually, if you believe that the result is not zero, you will get interaction constant. We have data files for scalars and axions because we also made some corrections for axion cross sections. And we have these files with data which may be directly used in experiments in archive. Calculations were done for sodium, iodine, thallium, xenon, argon, germanium atoms. So all we could think about in the recent detectors, but we can do it for anything else because program is running and we can do whatever we want. Okay, this is my first aim, and I just try to explain what we actually have done. So now I will not speak about models. There are many scalar models, popular models. A process which we consider absorption of scalar, which causes atomic ionization. So effect is similar to photoelectric effect, but it's a scalar particle. Scalar particle is absorbed and electron is emitted. So similar to photoionization. Of course, there are plenty of detectors which can see this, including xenon. Okay, so what is the problem? What people did incorrectly before? In a dominating multipolarity is zero multipolarity. At least it's expected to be dominating multipolarity in the process. And in the matrix element, you see these kind of wave functions. You see, it's F is upper component, G is lower component of Dirac spinor. And this combination here on the integral reminds us orthogonality condition. Therefore, this similar construction with only opposite sign of lower component give you orthogonality condition and must be zero. So when you can use plane wave approximation, it gives you very wrong result because this integral is not zero. So we can separate this parameter, orthogonality integral, from the formula, and we will, of course, we'll have extra terms. One term is just contribution of lower components of Dirac spinors, which contains alpha squared. And another term is because Bessel function here is actually varies. So it contains momentum of dark matter particles. It varies, so it's not exactly orthogonality integral. So, but this difference here is pretty small. It's momentum of scalar squared, radius squared over 6. So it's much, much smaller than 1. So both remaining terms are very small. So they strongly suppress dominating multipolarity. But when you do calculation with Born approximation, use plane wave for outgoing electron, with orthogonality condition is not fulfilled, you have very wrong results. This is just graph. This black curve shows you plane wave for outgoing electron, and the red curve gives you has a correct, in this case, Hartree-Fock wave, relativistic Hartree-Fock wave function. You see difference may exceed 8 orders of magnitude, because in matrix element error is 4 orders of magnitude, no, so like alpha squared here, 4 orders of magnitude correction, yes? And in probability, it will be alpha to the 4, so it's 8 orders of magnitude. So we corrected these mistakes. Also, we found that a similar pitfall exists for axioelectric effect. But in axioelectric effect, this orthogonality condition appears in a next multiple, not in dominated multiple, so effect is not so dramatic. Still, it's worth doing it properly. So Born approximation does not give you correct results even for axioelectric effect. You should do it more accurately, relativistic Hartree-Fock calculations. This is a reason why we have done complete relativistic Hartree-Fock calculations for scalars and axion and produced files which may be used in experiment. So these are these data point. And also is printed files. There are 4 curves here for 2 reasons. One of the reasons we consider both dark matter particles, in this case scalars, and solar particles. So, and the cross-section are different because for dark matter particles, we have non-relativistic problem, so mc squared equal to energy approximately. For solar axions, it may be ultra-relativistic. So difference between the 2 black curves is solid and dotted is for dark solar and dark matter axions. But we also know that there is a threshold for detection of electrons. So this blue and red curve are for including threshold. So it's only when outgoing electron energy is bigger than 1 keV, we count the result. So of course the result will be different in this case, but difference is just basically shifted curve, mainly shifted curve to initial point of 1 keV. So we did calculation for sodium, argon, germanium, iodine, xenon, thallium. So basically majority of detectors involves only these atoms. Okay, so the calculations were done again for both scalars and axion, and the data files are available. Also, there is interesting point that for solar axions, cross-section may be linked to photoelectric cross-section. So we can gauge our result. We can compare with calculations of photoelectric effect because they are more or less similar, and found that accuracy of our calculation is few percent. So it's more than sufficient for our purpose. So these results which we produced are very accurate. Of course, we also can calculate detection rate for scalar dark matter and for solar scalars. And comparing with Xenon one-tone data, we can extract interaction constant. If you believe that this peak at small energies is a real dark matter peak, you can extract constant interaction constant for dark matter scalar and interaction constant for solar scalar. No, they're approximately the same, it's to very good accuracy, something like 10 to the minus 14 if it's dimensionless constant. Okay, next we do not assume that it was real detection of scalars, but we can get a limit from the rest of dark matter data in Xenon one-tone. So on this Xenon are more or less comparable to limits, are much better than limits from fifth force, but they are comparable to this horizontal branch star cooling, a little bit less strong than RG star cooling, red giant star cooling. So the situation is more or less similar to axions. For scalar situation is more or less similar to axions in this case. Okay, this is second topic of my talk. It's about WIMPs. It's completely different type of calculation, but still we used relativistic Hartree-Fock calculations. Here we found another interesting thing. So for scalars, we got a strong suppression compared to naive results. Here we have strong enhancement compared to naive results. Because calculations were, old calculations were done in very approximate way with kind of plane wave approximation and so on for outgoing electrons. We did this properly, and we included relativistic effects. And what is amazing, relativistic effects increase ionization by WIMP scattering electrons by up to 3 orders of magnitude. So we did calculations for different atoms involved in dark matter detectors. What is also interesting, because of very small, strong dependence on momentum transfer, we have annual modulation due to variation of velocity of WIMP, up to 20 to 50%. It depends on mass of WIMP, of course, but it's very big. So even if the velocity change of WIMP is small due to Earth rotation around the sun, change of cross-section is pretty big. So we consider this effect. dark matter particles scatter on electron, and bound electron goes to continuum, so it's ionization. Okay, so again, previous calculation were not relativistic, a plane wave for outgoing electrons, and we did it properly. So why relativistic effects are so important? We know that in non-relativistic physics, an S-wave wave function for S-wave electron tends to constant. And you can easily find a limit of large momentum transfer for cross-section is 1 to the power of momentum transfer to the 8. But in relativistic case, behavior of wave function is different. It actually increases at a distance tends to 0. It even tends to infinity for point-like nucleus. And this changes the picture. Power becomes 6 minus 2z squared alpha squared. So decay with increase of momentum is very, very different in the relativistic case. So it's 5.7 in case of xenon and iodine, which are neighbors in periodic table. So it's approximately the same power. So power of 5.7 instead of 8, and gives you dramatic changes. So as I told, up to 3 orders of magnitude if in interesting area of momentum. So of course we derived the proper formula for this, and formula depends on atomic structure factors here with K. It was probably denoted by F in some previous talks. So the atomic structure factor, which is continuum, bound state continuum with factor I to the IQR, where Q is momentum transfer from dark matter particles to electron. Okay, so what we see here, this is just with atomic structure factors. For small momentum, relativistic and non-relativistic results are pretty similar. But if you go to big momenta, difference exceeds 3 orders of magnitude. And the typical momenta are here in the area of big momenta. If mass of a WIMP is heavy, some 100 GeV, for example. It's so if mass is heavy, we go to area of big momenta, and there is huge difference between non-relativistic and relativistic calculations. So these are pictures for different atoms, just as an illustration. Because it's relativistic effects, they very rapidly increase with the charge of a nucleus. So for sodium, this is lowest curve for cross-section. But if atoms are heavier and heavier, cross-sections becomes bigger and bigger. And again, because due to strong dependence on momentum here, we have big modulation, annual modulation of a cross-section. So these are results of Xenon collaboration published, which used our data. It's well known, of course, and indeed, using our data, we obtained big difference with the expected gamma result. So extrapolation from gamma result is in strong tension with the result of Xenon collaboration. Okay, so conclusion for this part of the talk. So relativistic Hartree-Fock calculations correct several orders of magnitude error for dark matter scalars and solar scalars. So for 2 types of scalars, which may be dark matter candidate or emitted from sun. Plane wave approximation does not work due to violation of orthogonality condition between bound and continuum electron wave functions. Error up to 8 orders of magnitude. So error is huge in this case. Such effect also exists for axions, but error is significant for small axion energies only. And the reason for axion with orthogonality condition works for subdominant multipole. We got new limits on electron scalar coupling from Xenon 1T data. We can even say that we get non-zero result if we assume that this peak in Xenon data is due to dark matter. We have produced data files for scalars and axions, which may be used for analysis of experimental data in different detectors for different atoms. Then relativistic effects increase ionization by WIMP scattering on electrons by up to 3 orders of magnitude. So it's completely different process. In the first scalar and axion processes, particle was absorbed. Here, WIMP of course survives, but it transfers momentum to electron and ionized atom. Plane wave approximation does not work, and annual modulation due to variation of velocity of WIMPs is up to 20 to 30, 50%. So we presented results for Dama, Libra, and Xenon collaborations, but since data files are available, the same results may be produced for any other detectors. Okay, in the remaining few minutes, I will describe some other works. It's a recent work which we submitted to archive, but in principle, we continue to polish it. It's about, first, it's about Migdal scattering, Migdal scattering of dark matter particles. So when dark matter particles hit the nucleus, nucleus shakes, start to move, and an electron may fly away. Then there is a result related to atmospheric dark matter particles. So why atmospheric dark matter particles? Is because cosmic ray may hit nucleus and produce mesons, which mesons decay to new kind of, some kind of dark matter. Reason why it's a different process is because velocity of this particle is maybe much bigger than velocity of usual dark matter candidates, which is 10 to the minus 3c. Here it may be much bigger, it may be even relativistic. Okay, so these are some calculations. I don't go into details, I just present the results. If someone interested may see a paper. So we considered this interaction and produced some areas, some exclusion limits on momentum independent dark matter nucleon scattering cross section for this kind of particles, which may be produced from, for example, meson decay, and it may be produced from dark matter. And we considered both this axion dark matter and boosted and Migdal effect. Boosted means that it's some high velocity component of dark matter. Okay, that's all about this part. And just few words about other possibility of studying scalars and pseudoscalars like axions. All effects which I discussed before contains second order or even higher order of interaction constant, because it's second order interaction constant with matter, because amplitude constraint first order and cross section second order, but there is also production of intermediate particles, which again contains two interaction constant. So it's all effects which considered before have high power of interaction constant with dark matter. Here, there are linear effects in interaction strength. Linear effects may be much bigger if interaction constant is small. For scalars, interaction with dark matter field produces apparent time-variant fundamental constant. So because we worked in this area of varying fundamental constant for a long time, we immediately jump on this possibility, and we improved the results for interaction of scalars with normal matter up to 15 orders of magnitude. Okay, but it's for very low mass of scalars. For pseudoscalars, situation is different because pseudoscalars interact with spin. So we have time-variant spin-dependent effects. For example, oscillating electric dipole moments, which usually are studied as a source of time reversal and variance violation. Here we do not have so dramatic improvements. It's about 3 orders of magnitude, but there are already 3 results of different collaborations. NEDM collaboration, Casper Electric, and GILA. It's results of Nobel laureate Eric Carnell group, who studied this interaction with pseudoscalar field by in experiments measuring electric dipole moments. So why variation of mass? Why we have dark matter causing variation of fundamental constant? It's just a convenient trick. For example, for mass term is proportional to fermion spinor. Yes, usual mass term. This is mass, this is fermion spinor. Interaction with scalar dark matter also proportional is interaction with same combination of scalar combination of fermion spinors. So we can combine these two terms into one and say mass varies. It's just a trick which allows us to do not perform new calculation, because we already calculated how atomic transition frequency depends on mass, for example, or fine structure constant. So, for example, if you consider here quadratic interaction with scalar fields, we have more rich physics, because cosine squared field, dark matter field is amplitude times cosine mt. Cosine squared gives you a constant term and term varying with double frequency. So constant term give you astrophysical observations, because it does not oscillate, but amplitude changes. And here it's amplitude of a scalar field squared. So you increase the volume of a universe, so density decreases. So it gives you slow drift of interaction constant. In this case, mass of a particle. But if there is oscillating term, it's a perfect place to look into laboratory variations. So it's similar. So mass give you interaction with fermions, give you variation of mass terms. Interaction with electromagnetic field, you give you variable fine structure constant. And there is also similar variation of mass term with in the case of bosons.
Victor, sorry to interrupt you. You have only 2 minutes left.
I'm finishing. So this is just illustration picture, what I've got here. This is limits from supernova energy loss for scalars. These are limits which we obtain from cosmic microwave background, Big Bang nucleosynthesis, dysprosium clock, and rubidium cesium clock. You see, gain is more often 15 orders of magnitude. And the gain appears because we consider linear effects in interaction constant. This is the reason of a gain. So very similar pictures for quarks, huge gain, similar picture for electrons, interaction of dark matter field with electrons. This is interaction of dark matter field with WZ boson. This is interaction of dark matter with Higgs boson. We always have a big gain when we use atomic experiments searching for variation of fundamental constants or dark matter fields. Okay, maybe I skip this term. This is about variable oscillating electric dipole moment, which also measured in experiments, in different experiments, and these are results of different collaborations for this. So a significant improvement in interaction of axion with gluons or nucleons. So conclusion for this part. Okay, maybe it's enough. I already showed this conclusion. I stop at this moment. Thank you.
Thank you so much, Victor, for this very interesting and informative talk. Okay, we have if anyone wants to ask question, just can raise the hand or turn on the microphone. Okay, if there is no question, let's thanks again to Victor, and we can move to the next speaker, Yasaman Farzan, who join us again. Yasaman, can you hear us? Could you please share your screen? Unfortunately, we cannot hear you.
Hello, can you hear me?
Yes.
Yeah, now I am trying to share my screen. Okay. Do you see my screen? Do you see my slides?
No.
No, we don't.
Do you see my slides?
No.
Oh my God.
Green button. You see the down, green sharing screen, green one.
Let me try share entire screen. Cancel.
Is it going well?
I'm trying to share, but I don't know why you can't see it.
This morning you did.
Yep, it worked. Now I'm clicking on share. No slides. Oh my God. Let me open it again.
Yasaman, can you hear us?
Yes, let me try once again. If I do not succeed, oh, I don't know why this is happening. Do you see it? Do you see the slides?
No.
Oh, sorry. It seems that I am not able to give the talk today. I apologize for this.
You cannot share. You have problem with sharing your screen?
Yes, I am clicking on window. I'm clicking on the slides, and I'm clicking on share.
Yes.
As usual, but you don't see it.
And you choose entire screen or window?
I chose entire screen. Let me try entire screen. Okay. Do you see the slides now? Because my screen is now full.
No,
I cannot see. Sheshin, can you see?
No. Yes, I will say.
I think something is happening now, it seems.
Something happening?
If you can maybe send me quickly, I can share for you.
Okay, I will send you an email, okay?
Send her file to you and then you share it now, okay?
Yes, if you send me quickly, I can share it.
I'm sorry for this technical problems. I have never encountered something like this before. It's a rather large PowerPoint. I hope that you receive it.
You send it right now?
Yes. But the file is rather large.
No problem.
No, send it by Skype if your file is very large.
No, Skype is even worse. I did not receive yet. Did you send to my IUT mail?
I sent to the same email address that I have received email from you. Yes, IUTAC.IR.
In the meantime, maybe you can try once more the sharing the screen, and Also, I am looking forward to receive the file. Ah, yes, I receive it.
Oh. This is not working because there is some exclamation mark on share screen. It seems that there is a problem. I don't know why.
Okay, 10 megs downloads. How much is that?
The size is 27.
Okay, it's finished. Let's go. Sorry, everyone. Now we can start. Just you can tell me to next slide, and then I will change the slide for you. Okay. Let me share the screen.
I apologize,
okay.
everybody.
Can you see my screen?
Good. Yes.
Can you see my screen?
No, I don't. I'm seeing.
Can you see my screen?
No, I don't.
No.
Unfortunately, I cannot hear you.
I see. Well, Professor. I see the slides, but there's something on it. Hello?
Yeah, but well.
Can you see my screen?
I see your screen, but there is something on top of it.
Can you see my screen, Yasemen?
Yes, this I see the slides in the background, but I don't see. But there is something on it. I think everybody else is seeing the same.
Shashank, can you see my screen?
No,
I cannot hear you.
I see something's wrong because you see the background as a fire, but it doesn't share really. Yeah. Everything, even the Skype. Something was not going correctly.
Try please to reduce the other screen. The okay, no.
Okay, now yes.
Okay, should I start?
Hello, why you call me? I see there's something. He's a fly. Yes.
Can you hear Yasemen?
Yes, but there is now another screen, Professor Shue's screen on the.
Yeah, but you okay? No.
Okay, let's.
Go ahead. Let's go ahead. Shashank, please turn on your microphone.
Okay, sorry for all these problems. And I would like to thank the organizers for giving me the opportunity and putting up with all this mess. I'm going to introduce a model that can simultaneously explain the excess observed by Xenon 1 ton and 511 keV observed from the center of the galaxy. Please turn the page. Next page, please. Solution, would you please go to the next? Okay. The talk is based on these two papers, one written in 2007, and I'm happy to say that although that paper was written to explain the 511 keV line, we also predicted a signal for xenon type experiments that later on was observed. Please next slide. Well, as you know, there is plenty of evidence for existence of dark matter through observing its gravitational effects. Next slide, please. Yeah, something like 25% of the total energy bodies of the universe is made of dark matter. But we have no clue what dark matter is made of. To learn about its properties, we should have alternative methods to study dark matter. If dark matter has some interaction with standard model particles, there will be, in principle, 3 ways to study dark matter: direct production at colliders, direct detection, and indirect detection. In this talk, I will focus on direct detection and indirect detection. Next slide, please. Well, this morning we heard in Ricardo's talk some news from Xenon Monotone on dark matter searches. Next slide. And we saw that Xenon Monotone has set a strong bond on cross-section of dark matter with nucleons. Moreover, next slide. Moreover, this Xenon Monotone has observed some excess of events at low energy beams of scattering of dark matter, which can be interpreted as a scattering of dark matter of electrons. Next slide. Although, as we heard before, it can come also from residual tritium decay. Next slide, please.
I hear some.
Although this excess can be explained by some residual tritium decay. Can you hear me? Okay. But still, it has excited the community, and as you know, many papers have been written on it. Next slide, please.
Solution.
Yes, I changed.
Now let me talk about the indirect dark matter search. The idea is to look for stable standard model particles coming from dark matter decay or annihilation. For example, if dark matter annihilation or decay produces photon, it can reach our detectors. And there is a rich program for detection of dark matter by indirect methods. Yeah, please, I explained this slide. Please go, please the next, okay. And there is a rich program for detection of dark matter indirectly with experiments all over the world. Every now and then, next slide, please. Every now and then, some of these indirect dark matter search experiments report some signal. Some of them, after a while, turn out to be just technical errors, some experimental errors, but some of them pass the test of time, and well, many papers in time are written on them, explaining them as a hint for dark matter, but after a while they go out of fashion. In my opinion, the reason why they go out of fashion is mostly, next slide, please. In my opinion, the reason why they go out of fashion is not that they are ruled out as dark matter evidence, but because theorists, the community of theorists, go out of run out of the ideas to explain them as the, dark matter. The ideas get finished. One of them is the 511 keV line. Next slide, please. Observed from the center of the galaxy, this 511 keV line has been with us for more than 40 years, and it can be, next slide, and it can be explained by annihilation of positronium atom. Integral The next slide, please. Next. Okay. Integral space, and next, I already, yeah. The integral space telescope had, please stop here. The integral space telescope has confirmed this signal with very high statistics, and thanks to its very good angular resolution, it has also reconstructed the morphology of the intensity of line from galactic center, which turns out to be consistent with some being proportional with dark matter density squared. Strengthening the hints for dark matter, the morphology. Next slide, please. Here you see the morphology of the line, the intensity relative to the distance from the center of the galaxy. Next slide. Although there are many proposals to explain this line within the standard model with different mechanisms, however, it is tantalizing to explain it as a hint for dark matter, because each of them have some problems. Next slide. In 2004, this group of physicists, this group of colleagues introduced a model to explain this 511 keV line by dark matter of mass of few MeV, which annihilates to electron positron with a cross section of 10 to minus 4 picobar. Next slide. But if the annihilation cross section is so large, then it will lead to reionization in the early universe right after recombination, and this will affect the CMB. And from careful study of CMB, some bounds are set, ruling out this solution as next slide, please. Next slide. Ruling out this solution as for 511 keV line. Okay, but this is under assumption that annihilation is constant in velocity. It is stable. Next slide. How about the case that the annihilation is p wave? Then dependence on velocity will be like this, meaning that the annihilation is large in the galaxy where velocity is relatively large, but at the time of recombination, when the dark matter pair velocity will be much smaller, then annihilation will be negligible. It will not affect CMB. However, on the other hand, at the time of freeze out, the annihilation cross section will be huge, which will suppress the relic density within the freeze out thermal scenario. Next slide. So we came up with this idea. In our model, dark matter is composed of a scalar particle of mass of MeV, or few MeV, which decays with a lifetime much greater than the age of the universe to some pico-charged particles denoted by C. These pico-charged particles eventually annihilate, producing electropositron that can lead to the 511 keV line. Notice that the C particles at the production will have will be relativistic and will have velocities much greater than the escape velocity. But thanks to their very tiny electric charge and the magnetic field in the galaxy, next one, please. Next slide, please. And the magnetic field in the galaxy, they can be accumulated. In fact, their Larmor radius, next slide, please. Their Larmor radius at the center of galaxy with magnetic field of 10 microgauss and electric charge of 3 times 10 to minus 11 will be something like 5 parsec, which is much smaller than the typical size of the galactic center. Next one. Next slide, please. Next slide, please. Okay, so here there is a few words on the nature of dark matter in this model. This dark matter can be identified with a slim particle which was introduced in these two papers. And its main decay annihilation mode is to neutrino antineutrino, and its abundance is set by standard freeze-out scenario. Now, how can we assign electric charge to this C particle? We should add an extra U1 gauge symmetry. I have not explained the. Would you please go back to the previous slide? Would you please go back to the previous slide? Anyway, when we add this new U1 gauge symmetry to the standard model gauge group, then C particles obtain a tiny electric charge, and in principle, ordinary particles, ordinary fermions, charged fermions can also obtain a coupling to the dark photon. Next slide, please. Now, in the limit that epsilon is equal to delta, the coupling of the dark photon to ordinary fermions vanishes. And as we showed in our paper, this has a consequence for A prime. A prime will have in this limit a very long lifetime, much longer than the age of the universe, and can be a subdominant dark matter candidate. Next slide, please. Slide number 35, please. Oh. Number 35, please. Okay. Then we should worry about the abundance of A prime. If its abundance too much, then it will overclose the universe. A prime particles can be produced by CC prime in the early universe, and notice that we are out of equilibrium. C and C bar never come to thermal equilibrium. Solving the Boltzmann equations, we found that the ratio of the density of the dark photons to ordinary photons is 10 to minus 4. Next slide, please. Then requiring that on one hand, A prime does not overclose the universe and does not affect BBN, we found that the mass of A prime, next slide, please. The mass of A prime is between 10 electron volt and 10 keV, and the coupling should be smaller than 3 times 10 to minus 10. The upper bound on the charge of the C particles comes from abundance of A prime and BBM bounds on extra relativistic degrees of freedom. Next slide, please. There is another problem. I emphasize that when the C particles are produced, they are relativistic, but thanks to their tiny electric field, the magnetic field in the galaxy will keep them inside the galactic disk. But on the other hand, as has been shown by Kolb and his collaborator, supernova winds can pump energy to these any charged particles, expelling it from the galaxy. You may wonder why this doesn't happen to electrons inside the galactic disk, because electrons have some mechanism for energy loss. So we should find some energy loss for C particles too. In fact, in the limit that A prime is stable, then it can act as a coolant. But what if delta is different from epsilon, and then A prime will not be stable? It will have a lifetime of something like 1,000 a year. Then we should introduce another coolant. Next slide, please. Next slide. And next, please. Okay. So let us denote the fraction of dark matter which has decayed with F. Previous slide, please. With F. This is the fraction of dark matter which has decayed to CC bar. And let us see what are the bonds on F. There are several bonds, but the strongest bond we found comes from a requirement that not all of CC bar particles inside the galaxy annihilate to AA bond, A prime dark photon pair. And from there, we find an upper bound on the fraction, which is 6 times 10 to minus 4. Next slide. Now we have these C particles with some tiny electric charge wandering around with relatively large velocities. Then they can interact with nucleons as well as any charged particle, nucleons as well as electrons, and they can leave such recoil energy on nuclei. Although the mass of the dark matter is few MeV, much smaller to impart large recoil energy, but because the C particles are relativistic, their recoil energy is noticeable. Next slide. Next slide summarizes all the bounds. Next slide, please. All the bounds on the model, which is devised to explain 511 keV line. You skip the, okay. And previous slide, please. Previous slide. Okay. Despite these bounds, if depending on the mass of the dark matter, if we evolve this horizontal lines that I have drawn, the 511 keV line can be explained. Next slide, please. Now, here we see the partial cross section of this C particles scattering, and since this is just a Coulomb interaction, it will have a very distinctive behavior relative to the recoil energy, which we can use in principle if we have enough data to distinguish it from ordinary beam scenario or even dipole or anapole dark matter. Next slide. Okay, the scenario has many interesting predictions. First, it can be tested by direct dark matter search, and then we predict some flux of positrons which can be detected by Voyager. More interestingly, if you remember, the density of C particles depended on the magnetic field in the galaxy. So the intensity of 511 keV line will be correlated with magnetic field in a galaxy or dwarf galaxy, and this correlation can be tested. Next slide. Now let us come to the main topic of the this talk, which is this xenon banton excess that we already heard about it. Next slide. Next slide. Okay. Remember that in our model, the dark matter particles decay to a pair of relativistic particles, charged particles accumulated by magnetic field. And there is energy pump from supernova wind, which will repel them from galactic disks. But we introduce, next slide, please, some coolant that will lead to energy loss by this C particles. We should balance the energy pump by supernova with this energy loss. Doing so, next slide, please. doing so, we find that the final velocity is something like 0.08 times the velocity of the light, of course, which is relatively large relative to the velocities of dark matter in the galaxy. Okay, next slide, please.
Just, Yasaman, I want to inform you that we are a bit out of time.
Yes, I can imagine. Okay, so please, then I will be quick. The maximum recoil energy of scattering of electron of this dark matter is given by this formula. It is proportional to velocity squared. Next slide. Next slide, please. In our model, C particles can interact with electrons via photon exchange or dark photon exchange in the limit that epsilon is much larger than epsilon minus epsilon delta, photon dominates. Next slide. Next slide, please. But in general, the cross-section will receive such correction, okay? If only the photon, yeah. Next slide. Next slide, please. If only a photon contributes, then this last data point, lowest data point which matches with the background cannot be explained. 2 slides, please skip the next slide and come to third, 55, please. But if we have such relation between delta minus epsilon and epsilon, both dark photon and photon contribute, canceling out their against each other in the first spin. So we find an excellent fit to the data. Next slide. Next slide, please. But what if this this is just this excess is due to tritium decay or something? Then we should interpret this data as an upper bound on F, the fraction of dark matter particles that have decay. Interpreting as a bound, we find the fraction is smaller than 10 to minus 6, but still, even with such small values of F, we can explain the 511 keV line. Thank you for your attention. Please go to the slide of 57 so that, yeah, 57, please, my summary. Please.
Okay, this one is 57. Can you see that?
Okay, let us summarize. We introduced a model based on decay of MeV dark matter to a pair of pico-charged particles. Magnetic field of the galaxy can accumulate C particles in the galactic disk. C particles in relativity can leave a significant recoil energy on electrons, which can explain xenon one-ton electron excess. It can also explain the 511 keV line. And we have a lot of interesting predictions that can be tested. I didn't have time to go through all of them. Thank you for your attention and sorry for the technical problems.
Thank you so much. Unfortunately, we have no time for the question. We have to move to the next speaker, which is myself and Sheshen. Thank you, Yasaman, again. Okay. Sheshen, can you hear me?
Yes, I'm ready. Okay.
Okay. Please go ahead.
Yeah, but you should
Okay.
put a screen. Share your.
Yes, here is the screen. Can you see?
Yeah, I do. But it's not our presentation. It's the one by previous speaker.
No, it is. You can see now.
No, you are still in the presentation of the
No, it
previous.
changed. No, it changed. It changed. I can see.
I cannot. What? Oh, dear.
I still see my own summary, nothing new.
Yeah, I saw her summary. I don't. Hello, Soroush.
No, can you see again or not still?
I saw her
Okay.
summary.
Okay, let me share again. Let me share again. Don't worry.
You restarted.
Okay, no, can you see?
Yeah, now I think it's coming. It takes some time.
Can you see the slides? You have to see now.
No, not yet. How about other people? Can you all see the screen sharing?
No, I cannot see the actual screen.
Let me do again. I don't know what happened today. Okay, what about now?
No. Oh, it's coming. Okay, but I think there's some. So I think I have your file, don't you? But there is no last version.
Maybe I have to go and come back. Let me just a moment. Okay, I again share. Can you see now? Shashank.
Oh, yes, now it's coming up. Okay, so.
Okay. Okay, please go ahead.
Okay, thank you everyone for your patience. Solution I take this opportunity to share you our idea and scenario on particular on new physics beyond standard model. But here we are focused on dark matter particles, in particular in sterilized neutrino. So next slide. So all we know, the standard model law has been so successfully. Still, theoretically, there are many unsolved problems. For example, like mystery of the particle generation. Why do we have 3 generations? And origin of the mass of the fermion, in particular neutrino masses, and also this hierarchy problem of the mass from the top quark to the neutrino mass. And the other thing, it is related to fine-tuning or the strong CP and so on, neutrino. So these are all theoretical issues. Apparently needed new physics beyond standard model. Recently, from the experimental point of view, we have many progress in experiment, which telling us something that shedding light to solve the problem of theoretical issue. One of them is just recently Xenon experiment. It's coming up on muon G-2 and mini-bond access and all the and the B-meson decay just recently. So this one part theory, the other part experiment. So our views or our philosophy for this modeling this physics beyond standard model is based on the UV physics hypothesis, and then we use most of the logic in base of the Occam razor. Next slide. Next slide. Okay, so we have in UV, there must be some new physics which beyond the standard model. For example, due to the quantum gravity or gravity, so at that UV level, due to the quantum gravity or other new physics, all the fermion from the top quark and then stellar neutrino or neutrino has to behave the same. So this new physics should introduce effective new interaction like this of Lambo-Ioannina. Okay, this one Lambo-Ioannina 4 fermion interaction. This 4 fermion has been studied many years ago, and then he introduced dynamic symmetry breaking and generating a top quark mass. And this is so-called, in one hand is called Higgs mechanism, the other you call Lambo-Ioannina model. They are equivalent in low energy. Okay, this is one in a standard model. Okay, let's go on. So here in go to low energy, actually this model was studied before the Higgs particle was discovered. And that time there's no enough information, experimental information for theory. After Higgs particles is discovered, we can really study this effective Lagrangian. And we found there's something happens in the TV. So all this effect Lagrangian, all everything fixed, and then if we implement the experimental value of the top and Higgs particle, we found something happened in the TV. Okay, so means something happened in TV in that sense that the theory is not theoretical self-consistent. There's something must happen at TV. So what's about that? So this has been studied. Now let's go to the next slide. Okay, next slide. Next. So now we are not going to discuss this carefully. I just give you information. Something must be happen in TV, about 10 TeV. So as I mentioned from very beginning, this whole study is just focused on top quark. Okay, by this Bardeen here, all this company, and then Lambo-Ioannina model is just exactly Higgs mechanism. So now, if we're thinking about this same mechanism for stellar neutrino, because I said from the very beginning, new physics at the high energy scale should not make any difference between the top and stellar neutrino, because they are at that high energy level, they look like a massless particle. So this new physics should play the same role in the top quark channel for Higgs mechanism, and also the dynamic, also same dynamic for the stellar channel. So you see, we have 4 stellar interacting like one study in the Higgs mechanism. However, now it's stellar neutrino channel. So now the symmetry here is no longer standard model gauge symmetry like a Higgs mechanism. I put a sample Higgs mechanism. However, it's also called lepton, U1. So the same dynamic happens. Okay, then this stellar neutrino generate Ioannina masses. So as a theorem of Gordon-Stone theorem, you have a massless mode, so pseudo-scalar, which is actually action. So this come up at 1. So now let me emphasize, we are focused on dark matter particle. So now, so far, our candidate of the dark matter particle is 3 sterilized, one of the 3 sterilized neutrino. Family 1 sterilized neutrino 1, sterilized neutrino 2, sterilized neutrino 3. Okay, this is one of the dark matter candidate particle we're discussing. Now, after this mechanism of the Higgs mechanism, however, apply in a sterilized neutrino, generated Ioannina mass of the stellar neutrino, there's 2 composite particles appear exactly like in the Higgs mechanism. One is this pseudo-scalar, which actually is action. We just informatic this actual action. This is something like in a standard model, which is Gordon-Stone mode. Eton becomes longitudinal mode of the W and G boson. But however here, because stellar neutrino has no gauge coupling, so that's why this pseudoscalar mode, very light pseudoscalar mode, is just present in the ground state, play the low like very extremely light actions. In the same time, same thing happened for the Higgs. The Higgs here, you found that some very massive scalar boson, which is a condensate of a sterilized neutrino. So you see, this condensate sterile neutrino is about 100 GeV. So it's very similar like Higgs. An action, a pseudoscalar action, we pay the similar like Gordon-Stone mode eaten by W and G. But here, this action is not eaten; it just travel free in the ground state, pay the low like action. Okay, next slide, please. Okay, so this effect of grounding, I just explained you that is the same as top quark Higgs mechanism. Hello, however, it's for sterilized neutrino. So here we have two additional sterilized one is action, particle.
No, sta sotto, penso alla punta.
The other is
open.
The other is a massive ship. The other is a massive ship scalar particle, which play the role like a wind particle. And exactly his counterpart in the Higgs mechanism is Higgs. Next slide, please. And in addition, okay, I summarize, we have 3 sterile neutrino as a fermion candidate dark matter particle. Now we have, and then whose Majorana mass is generated by spontaneously breaking like Higgs mechanism. So there's 2 composite particles appear. One is pseudoscalar, which is paid by action, very light. The other is massive Higgs-like particle, the composite by stellar neutrino, whose mass is almost same as Higgs mass. Now, in addition, due to this interacting, okay, we will introduce this sterilized neutrino and this action and other part, this sterilized sector coupled to standard model particle by, for example, by this sunlight diagram. Next slide. Next slide, please. Okay, I give example. For example, now the gauge boson we have is just like the one in the standard model. There's no dark photon. There's no something else. It's gauge boson of the standard model, WG and photon. And due to this 4 fermi interacting, they induce irreducible, one particle irreducible interacting vortex with the stellar neutrino N and standard model. So you see there are 3 types, okay? So here is just the same as standard model. However, now there's this coupling, of course, very weak, and we'll make a constraint of it. This particle interacting with stellar neutrino and actions, all this with WG photon and other particle of standard model. So masses, the scale is the same as a standard model scale, energy scale. Okay, this low energy scale. And then the coupling is, the additional coupling is dependent on the scale of the new physics. Next slide, please. So these are basic building block. From the UV, we have all these induced interacting vortex with the parameterization ready for examining new physics which are going on, new experimental phenomena which are going on. So now I pass to the Soroush for detailed explanation. Soroush.
Yes. As Shesheng mentioned, this is one of the peculiar signature of our model, which is the a new electromagnetic vertex between neutrino, a standard model neutrino, sterile neutrino, and photon, which can give us so many phenomenological aspects, whether in the astrophysics or in the ground-based experiment like the Xenon experiment. So here you can see, as this sterile neutrino, which is a beyond the standard model particle, coupled to the standard model particle, it is important to check this the consistency with the standard model precision test. One of them is the W decay. As you can see from the W decay width, we can put a direct constraint on the right-handed coupling of the right-handed neutrino, left-handed leptons, and also W bosons. You can see here this GR is less than 10 to minus 3. And also the point is, as these sterile neutrinos can couple to photons, it can give some contribution to the vacuum polarization and photon vacuum polarization. And it can modify the fine structure constant. You can see here the constraint that comes from the standard model precision test on the alpha. So this I'm going to tell you about how we can find the signature of this new type of the sterile neutrino in the Xenon experiment, or whether we can explain this new signal of the Xenon based on this effective model or not. So I can skip this slide because just explain the other candidate of the dark matter, WIMP and Axion. As we already mentioned, these are included in our models. Here you can see the sterile neutrino, and we know the mass range of the sterile neutrino is something between few keV to some giga electron volt. And they can mix with the standard model neutrinos, and they are known so far by so many authors. And the point is, these keV mass sterile neutrinos are overproduced in the early universe, which I will come back to this issue in the future. And another point is, as you can see in the spectrum of the neutrino here, in the plot right-hand top, there is a missing part in the spectrum of the neutrinos. So it can be a hint of some new generation of neutrinos, which is sterile neutrinos. So already in the previous talks, we have some explanation of this new signal of the Xenon, which appeared at the low energy scale. So I'm going to tell you why this new sterile neutrino that we introduced can well fitted with this result. So Xenon is a direct detection experiment which is on the Earth, and Earth going through the dark matter halo. Here you can see the dark matter flux and the dark matter density. For example, for a mass around 100 keV, you have 10 to 14 the flux of the sterile neutrino. So the point is, we have two kinds of scattering, as Gili explained us in the 3 talks before. We have elastic and inelastic scattering. You can see here in the elastic scattering, there is some energy change between the incoming and outgoing particle, which is the difference of the kinetic energy. And you can see here it cannot produce so much recoil. For example, for the mass around 2 mega electron volts, you got just 2 electron volts recoil, and you have so much technical difficulties to detect such a recoil. Or a strategy here is used in elastic scattering, in the process in which we have absorption of the dark matter particle and then emission of the electron, something like this process that I showed you in the right-hand side of this figure. And the kinetic energy exchange in this process, you can see, is around the mass of the particle. You can imagine a dark matter can be absorbed by the electron and then emit a normal neutrino and electron, and we can have such an interaction in our model based on the vertex that we introduced in the previous slide. Here you can see we could have incoming sterile neutrino and outgoing electron and neutrino. So here we classified all the process which can be offered based on our model. So here you can see the cross section of the recoil cross section of this interaction that I showed you in the left top. Interestingly, you can see this energy dependence. When you go to the low energy, you got some enhancement. So it gives some hint to explain this enhancement in the xenon signal. Here you can see another plot which showed you a sterile neutrino can be absorbed by electron and outgoing is electron, and the right hand and the sorry, here I have to write the left hand, a normal neutrino. So here you can see a summary of our result which shows you 3 types of the sterile neutrino that we proposed: the electron sterile neutrino, muon sterile neutrino, and the tau sterile neutrino can fit the xenon data by the mass around 90 keV and the coupling around 10 to minus 4, 10 to minus 7, and 10 to minus 8 for the different generation of these sterile neutrinos. So I think I'm going to finish my slide. Just I would like to comment on some astrophysical and cosmological constraints that our model respect to them. If we demand to have dark matter sterile neutrino, the lifetime of that particle should be larger than the lifetime of the universe. And also, according to this new electromagnetic vertex, we could have some energy loss due to these new interactions in the stars. We showed that our fitting for xenon result can preserve both the astrophysical and cosmological constraint. As final to a slide, just I would like to mention that our model can solve the long-standing problem of the relic density of the sterile neutrino. We know so far that the sterile neutrino around the keV can be overproduced, and here you can see the first plot, for example, first equation, for example, for a 90 keV neutrino, we have around 240 for the omega n, which is around you can see is much higher than the value that the Planck tell us. So what will happen and how our model can solve this? We have other generation of the sterile neutrino which can simply decay due to the higher mass, and this produce some dilution factor, some entropy in the radiation part, and in this sense we can solve this issue of the relic density. We have lightest particle, for example, the sterile neutrino electron could be the dark matter, and the other type, that muon and tau sterile neutrino, can decay and can give entropy to the radiation. So as we showed, there is a degeneracy between different generation of the sterile neutrino, and all of them can fit the xenon data. So how we can break this degeneracy? The point is, by upcoming experiments like Xenon NT and Darwin, we showed in our paper that we give some new prediction which can solve this, which can break this degeneracy. And also we have different anomalies in the particle physics which recently and so far appeared, like G-2 muon, minimum anomaly, and B meson decays, that we are working on them, and we have some good estimation that our model can at the same time solve different anomalies. And this is my talk. Thank you for attention, and sorry for going a bit out of time.
So good. So we thank all the participants this morning and all the speakers, of course. We have a good time to share the idea each other. And now it's time to close section. So please say something. And if
yes, thank you everyone, and sorry for some technical problem that happens, but you know, always this live and virtual meeting may be faced with some problem. Let me to just open my video to thank everybody to be with us, and we hope we continue our discussion, and we have your proceedings and your contribution. And also we kindly ask all of these speakers to upload their presentation in the web page. Okay.
In this way we can continue discussion.
We didn't hear all the talks though.
Yeah. Yes, I think Carlos is not with us. Sheshen, Carlos is with us or is not with us?
Sorry? We finished.
Carlos is with us or is not with us?
Carlos, he should be on his job. I mean, I don't know. I have no idea about him. But
okay, so we can maybe continue with Lilia. Carlos, are you there?
Yeah.
Gregory is there maybe.
Who is there?
So we give the stage to you, Gregory, or we can continue. We have no problem.
No, we need to find a
I
Carlos.
am not speaking at your session.
No,
okay.
Carlos.
Because Carlos is not here, but Ilya is here. Ilya, I think we can pass this to Ilya to present his talk, because I canceled the sharing. Ilya, can you share your screen, please?
I will try. Thank you. Okay. Can you see my screen?
Yes.
Wonderful.
Yes.
Okay.
Okay, please go ahead.
So here it is, the full, and you can see the full screen mode, right? Yes. Thank you. So my topic is quite different from what we've been listening to so far today. It is about dark matter, but it's not about dark matter particles, but about dark matter halos. And so you'll have to switch mental gears a little bit here. We're talking about the whole halos and how they relax and come to equilibrium from the theoretical point of view. So specifically, I will talk about our theoretical model that we have developed to describe approach to equilibrium for idealized collisionless self-gravitating systems, meaning dark matter halos in practical terms. And this work builds upon a published model that describes equilibrium configurations of dark matter halos. It's a theoretical model, but it describes n-body simulations. It explains the results of n-body simulations. So I'll start with equilibrium systems and then move on to approach to equilibrium, so evolution. Okay, so it's been known for a while that collisionless collapse of self-gravitating systems like dark matter halos results in nearly universal system. So the density profile is nearly universal. And this goes by the name of an FW, Navarro, Frank, and White profile, and many groups have verified this result. And on the right here, you can see that the profiles do not depend much, the density profiles do not depend much on the initial conditions. You can start in different types of cosmologies and you'll end up with the same type of a profile. So even though numerical results have converged and everybody agrees on them, there's no good theoretical explanation for why that shape for the profile and why it is so universal. And many attempts have been made, and I have a partial list of papers here, but none of them have really fully succeeded. But many authors have noted that the fact that dark matter halos have a large number of particles suggests the use of statistical mechanics. And furthermore, universality of the equilibrium state suggests that the final state may correspond to the most likely state, which means that one might want to use maximum entropy arguments. And what I'm going to do, what we did in our work, is use statistical mechanics and maximum entropy arguments. So density profiles are interesting, but in StatMech, we deal with energy distributions. So by energy, I mean, and this is non-relativistic. So by energy, I mean kinetic plus gravitational potential energy of particles. Now, if you're familiar with standard statistical mechanics, you would know that the quantity that they use is the distribution function, f of e. What we're using is n of e, which is a product of the distribution function times the density of states. So this is n of e is the differential energy distribution, or just I'll call it energy distribution. So why do we use n of e? The reason is because in an equilibrium collisionless system, each particle's energy is fixed. It is not changing. That's the nature of collisionless. So it makes sense then to partition the state space not as a phase space, but as a space of energy. So if we're using partitioning in energy, then n of e is the quantity to use. And that's what we'll do from now on. Also, this differential energy distribution gives the full description of the system. For example, you can derive the density distribution if you have the distribution in energies. Okay, so a successful theory must reproduce n of e of equilibrium n-body halos emerging from n-body simulations. And what I have here is just that distribution. So this is from millennium n-body simulations, and this is an equilibrium halo. On the horizontal axis, you have dimensionless energy. And the vertical axis is log of n of e. And this is what that distribution looks like. So this end, the left end, is the most bound particles. So there's nothing, there are no particles existing at even more bound energies. And the most bound particle is the particle that has zero kinetic energy, and it's sitting at the very bottom of the potential well. So it's the most bound particle. On the other hand, on this side, you have less bound particles. So these are on the outsides of dark matter halos. And in any cosmological setting, it's going to be less virialized stuff. So there'll be material infalling, possibly smaller halos that are interacting. So this part of the energy distribution is not well virialized, and any theory, you wouldn't expect a theory to describe this end pretty well. But this end should be described very well by any theory that you want to come up with. Okay, so n-body halos are quite complicated. So in this work, we're also going to work with a simplified numerical approach to describe collapse and virialization of dark matter halos. And it is called Extended Secondary Infall Model, or ESIM. It's basically a mean field model, which is spherically symmetric. It has radial forces only, and the phase space, instead of being 6-dimensional, it is only 3-dimensional. So there's one spatial and 2 velocity components. And during the collapse, during the spherical collapse, radial and angular actions are conserved for each particle. So some of what I will present has results from this. And this is the energy distribution for ESIM, for these idealized collapses. And finally, let me present the result of our theoretical model, which I'll describe in a second, but first I want to show just the energy distribution. And this is it. And you can, the three past slides, the energy distributions of all of them superimposed is shown here. And you can see that they look very much the same. And especially at this end, which is virialized, this is the virialized and relaxed end of the energy distribution, and all three agree. And so what that means is that, first of all, that eSIM, this idealized collapse, summarizes the essence of physics going on in full n-body simulation. So we are justified in proceeding with just eSIM. And also DarkExp, which I will explain next, which is our theoretical model, fits them very well. Okay, so now I'm going to describe our theoretical model. And in fact, I will present to you the entropy, our expression for the entropy. And it is a simple theory, and the whole derivation is summarized on this slide completely. And most of it will actually sound familiar to you if you had a college stat mech. So entropy is related to the number of microstates corresponding to a given macrostate. And a macrostate is fully described by this distribution of energy. And so what we want to do is to describe the shape, to derive the shape of this NOV. This counting of the number of microstates, this big W, is again familiar to you. This N is the same, we assume that it is the same as this N. Now in the standard stat mech, this N is identified with the distribution function. But for collisionless systems, we identified with the energy distribution. And this is the only actually conceptual difference from the derivation, the standard derivation of the Maxwell-Boltzmann distribution. Other than that, it's pretty much the Maxwell-Boltzmann distribution derivation. So as usual, we take log of W, this occupation number, and because we're interested in the shape of the distribution, the terms that have to do with the normalization, so the total number of particles, can be gotten rid of. And also the degeneracy of levels is constant. So these two terms are irrelevant, we throw them away. So this is the only term which remains. And we went from factorials to describing them as gamma functions. So that's that. Now to find the most likely state for the fixed total energy, we define our entropy as S sub D. D stands for DarkExp, and S is the standard notation for entropy. So it consists of two terms. The first term is this one here, and the second one is the Lagrange multiplier that goes with fixed energy. So just these two terms. And so now we rewrite in terms of, instead of a sum, we write integrals. But other than that, it's these two are the same thing. So this is our entropy. This is how we arrived at our entropy. Now, if it is a good entropy, if it is a valid definition of entropy, then if you maximize it, you should get that should describe the final state of equilibrium systems. And in fact, if you do the standard algebra and you basically differentiate that with respect to n and set it to 0, which gives you an extremum, you get this equation. And this is N of phi that we sought here. And it is proportional and not equal because the proportionality, this number up here, is just normalization, and it's not interesting. It's just the shape that we're interested in. And you can also show that it is actually a maximum by taking the second derivative, and you can see that it is in fact less than 0. So this is our expression for N of phi. And if you plot it, so it's a very simple thing. It's exponential -1, and exponential part is this part, and -1 gives rise to this truncation. And this is what I had plotted previously in magenta. Okay, so it fits what n-body simulations give us. So this is great, but if this entropy expression is a good entropy expression, it should also do one more thing for us. It should increase with time, just like as you would expect for entropy to increase during evolution as the halo evolves. And I will show that this is in fact the case on the next slide. So here I'm using the simplified collapse, this extended secondary infill model. And the top plot here, the vertical axis has this expression. That's what I'm plotting here. the horizontal axis is time, so cosmic time, so log of it actually. So this is when the universe was about 1/100th of its current age, and this is today. And this is this quantity. So you can see that it is increasing monotonically, and it approaches the dark X value at the present time. Okay, so it does what entropy is supposed to do. It's increasing with time. The bottom row here shows how the shape of the energy distribution evolves with time. And just to guide your eye, this is dark X, this is that shape. And so early on, the shape of the NOV of the cesium halo looks nothing like dark X. But as the time goes forward, the shape changes and it finally reaches our prediction. So you may wonder whether this particular halo was chosen specifically to match our theoretical results. And that's not the case, because here I'm plotting not just the halo that I showed on the previous slide, which is in this blue curve, but a total of 6 halos. And I could have plotted more, but you know, it'll be too overcrowded. So the vertical axis is this SD, entropy. And for each one of these 6 different halos, it is increasing. Each one follows a somewhat different trajectory because they had different initial conditions, but they all increase monotonically and they asymptote towards dark X shape. And here for 2 of these halos, as examples, I'm showing their evolution as a function of time. So the lighter shades of blue and green show you what happens early on, and then the shape changes. And at present epoch, for virialized halos, it reaches dark X. Okay, so many cesium halos with different initial conditions asymptote to the same shape at equilibrium. So this is a short talk. This brings me to my conclusions. So dark X is derived using principles of statistical mechanics, and the derivation is very straightforward. There's just one conceptual difference compared to how Maxwell-Boltzmann statistics are derived, and that's the fact that we interpret the occupation number as distribution in energy as opposed to the distribution function. And so with that, we arrive at the distribution in energies, and it is followed very well by n-body simulations as well as our simplified collapse. And even though I've concentrated on the energy distribution, the density profiles and velocity dispersion profiles predicted by our model also satisfy n-body simulations as well as the simplified collapse. And so the equilibrium state is satisfied, and the entropy does what entropy does. It increases as a function of time, monotonically. And so this is a self-consistent theory. It explains the final state as well as approach to equilibrium. Yeah, so thank you for listening. And I know this is very different from the particle physics that we've had in this section, but I appreciate your attention. Thank you.
Thank you so much, Ilya. Thank you to be exactly on time.
Yes.
You know, in contrast to me, that was the chairperson and I went out of time. So we have time for a couple of questions. Anybody has any comment or questions are welcome. So if there is no question, we thank you again and we can move to the next speaker. ICRANet, if I true pronounce ICRANet. Can you hear me? ICRANet?
Yes, I hear you. Oi.
Yes. Please share your screen and go ahead.
Okay, just a moment. Do you see my screen?
Yes, we can see. Go ahead. Please go ahead.
Is it
Thank you.
normal or something?
No, it is okay, but I think it's okay. Can you
Sorry,
change
it's
the slide?
impossible to list it. I'm
I think it's
sorry, it is
okay.
impossible to list presentation. So let's see it inside of PowerPoint. Seems to me
No,
it is normal.
that was okay. You can,
Okay.
yes, you can make it full screen and.
Unfortunately, it is problem with full screen.
Okay, no problem.
I can't list it.
Okay, you can continue whatever you want. Is okay. Both is okay for us.
Oh, okay. So, okay. My talk is about preliminary results of rich galaxy clusters spatial distribution analysis on CFA2 redshift survey data. And the question occurs, does we see compact objects or dark matter presence at redshifts less than 0.022? Clusters of galaxies reveal an independent approach to the problems related to distribution of matter and various redshift range. Galaxy clusters are the biggest gravitationally bound system. It is possible to use such system to constrain cosmological models and to understand process of galaxies and galaxy clusters formation connected dark matter halos. So, the difference of galaxies were identified by their luminosity, morphology, color, and so on. And investigators of such properties allow studying the relation between the topology and properties of galaxies at large scaling structure. So, and in this case, we can conclude both cosmological parameters and galaxy formation mechanism. Moreover, the investigation of galaxy clusters also relate to independence of characteristic of galaxies to the surrounding medium properties and the large scaling structure formation. So, thus, if we investigate cluster system dynamic, in this case, we can possibly estimate dark matter presence due to analysis of several catalogs. For example, the second CFA redshift survey. So this slide represents galaxies distribution accordingly to the second CFA redshift survey data. So this catalog was started between 1985 and 1995 during measurements of relative distance via redshift for about 18,000 bright galaxies in the northern sky. It contains data of 1917 galaxies group, a total approximately 6,787 members at galactic latitudes bigger than 20 degrees. So then we have analyzed properties of several galaxy clusters. The mean parameters for such clusters seen in this table. So you can see that amount of galaxies is more than several tens, and we try to analyze spatial distribution of such clusters. When we construct such distribution, we can see that several peculiarities have found on spatial distribution. Is it real dual structure of this distribution or not? So let's see next slides. These distributions for cluster 1 1046 and 1042, and this distribution reveals the same structure. The same structure for clusters 142 and 1933. Sorry. Oi. Then the same distributions for clusters 1652 and 316. So this slide shows the example of peculiarities in distributions of member of galaxies clusters on magnitude and absolute magnitudes. This example for cluster number 142. As an example for these clusters, this example shows peculiarities in absolute magnitude distribution on angular velocity and distribution on velocity of galaxies and distance to cluster center. So if we consider that it is a real dual structure, we have bifurcation points in the values magnitude is equal 14.5 and absolute magnitude is equal 19.5. So, and sorry. Sorry. So, and we can see two bifurcation point in distribution which shown on this slide too. This point correspond to distance to center of cluster is equal 0.7 megaparsec, and of course absolute magnitude 19.8. It corresponds to absolute magnitude 19.5, which was found for previous slide. So this is example for cluster number 88. We can see two bifurcation point and on this distribution and on this distribution too. Then we can see the distribution on group member position, absolute magnitude and luminosity, represent two areas for clusters numbers 88, 1101, 1046, 142, 933, and so on. In the redshift of this cluster are in the region 0.002, from 0.002 up to 0.022, and galaxies from these areas are paired accordingly its spectral characteristics and position. So, and in this case, question occurs, is it a real dual structure or it only seems to us? So, we can try to make analysis of phase space of these systems. Let's try to construct phase space using values of redshift, coordinates, absolute magnitude, and distance to center of cluster. And we must to find values which we will use instead time. So let's try to use velocity as time similar variable. And then we try to investigate dynamic of system in such phase space. We try to construct simple attractors. Let's separate bosons of attractors correspondingly to bifurcation points, which we found for previous slides. So, and then you can see. So, this is example of for clusters number 88. You can see that two-dimension and three-dimension projections of phase space shows that two attractors possibly be constructed. So it is a real dual structure. This slide shows other projections. Dual structure occurs. It is a real dual structure. Do you see my mouse? So you can see this.
Yes, we can see that.
And this system. Okay. And this system and this system, there are really two different attractors. So, and next questions occur. Does such structure follows by object with high energy emission? Because of when we have analyzed Fermi catalogs, we find association of cluster number 1933 and one of sources, and we find association of cluster 1046 and other objects. All of these objects observed in sub-TV region by Veritas 2. So, and estimation of flux in the energy band from 1 to 100 GeV make this object possible to include in program of observation of the planet Gamma telescope Gamma 400, for example. So then conclusions. I present preliminary results of the investigations of properties of 14 clusters of galaxies from CF82 redshift survey, with redshift in the region from 0.02 up to 0.022. So, analysis of the distribution on magnitude, absolute magnitude at angular velocity, and other distributions together with spatial distribution represent two areas for these clusters. When we try to construct attractors, we see that these are real areas which caused by dynamic of this system. So, in this we receive question, how occurs such structure? It is possible dark matter presence inside cluster in configuration similar to the Zeldovich pancake, for example. So, or maybe we seen gravitational lensing on compact object which located between galaxy cluster and observer. Also, it is possible to be dark matter blob between galaxy cluster and observer too. So, moreover, several groups, 4 groups, reveals association with high-energy gamma emission source on Fermilab 10-year point source catalogs, and 2 of them observed in sub-TeV energy by Veritas data. So in this case, it will be better to organize joint observation of such cluster by orbital gamma ray observatories with high angular resolution, and for example, ground-based Cherenkov air shower experiment. So this situation could possibly clarify the type of influence to group characteristic. Was it gravitational lensing or it is dark matter object inside cluster? And we can study processes of particle acceleration in this object and how formed high energy emission of such object. So thus we propose including these and similar clusters in the programs of observation of the planet experiment Gamma 400.
Thank you, Irene. Actually, we are. Can you hear me, Irene?
What?
Can you hear me? I mean, we are going out of time.
Okay. So,
okay.
And last word, it will be nice to coordinate these observations of multi-wavelength observation program of Cherenkov telescope array. So that's all.
Thank you so much. Thank you so much. Actually, we have no time for the question, but if someone has question, can type in the chat. And Irene, please kindly, if you see any question in the chat, please follow them and answer them. Thank you. Thank you so much. So we move quickly to Pierre-Henry Cavanis. Pierre-Henry, can you hear us?
Yes, yes. I will try to share the screen.
Okay.
Is it working?
Yes, I think something is coming. Yes, it's perfect. And please go ahead. And I think based on the timetable, we can have exactly time of your talk. Don't worry about that. Follow your time and go ahead, please.
Okay. So I will discuss the mass-radius relation of self-gravitating Bose-Einstein condensates with repulsive or attractive self-interaction. And I will apply these results to the case of boson stars and dark matter halos made of Bose-Einstein condensates. So first, I consider the case of non-relativistic Bose-Einstein condensates at 0 temperature. So in that case, all the bosons have condensed, and the system is described by one order parameter psi, which is called the condensate wave function, and which is governed by the Gross-Pitayevsky equation coupled to the Poisson equation. So the Gross-Pitayevsky equation is a form of nonlinear Schrödinger equation, which involves a cubic nonlinearity, which takes into account the self-interaction of the boson. And AS is the scattering length of the boson, which can be positive or negative. When AS is positive, we have a repulsive self-interaction, and when AS is negative, we have an attractive self-interaction. So by using the Madlung transformation, it is possible to transform the Gross-Pitayevsky equation in terms of hydrodynamic equations, which are similar to the usual Euler equation, except that they include an additional term, which is the Bohm quantum potential, and which takes into account the Heisenberg uncertainty principle. There is also a pressure force, which is due to the self-interaction of the boson, and which is given by this relation. So it corresponds to a polytrope of index n equal 1. And when the scattering length is positive, we have a positive pressure, so a repulsion. while when the scattering length is negative, we have a negative pressure corresponding to an attraction. So the condition of quantum hydrostatic equilibrium expresses the balance between the pressure due to the self-interaction, the gravitational attraction, and the repulsion due to the quantum potential. And if we combine this condition of quantum hydrostatic equilibrium with the Poisson equation, we obtain a differential equation which gives the shape of the density profile at equilibrium. So let us first consider the case of non-interacting boson. So in that case, the differential equation reduces to that form, which can be solved numerically. So we get the following profile, density as a function of the distance. We can also obtain the mass-radius relationship, which is given by this expression, showing that the radius decreases as the mass increases, and it scales like 1/m. Finally, in order to describe ultra-compact galactic halos with mass 10 to the power 8 solar masses and radius about 1 kpc, with this Bose-Einstein condensate dark matter model, we need a very small boson mass of the order of 10 to the power minus 22 electron volt. So this could correspond to ultralight axions. And this kind of dark matter is called fuzzy dark matter. If we now consider the opposite limit, where we have a strong repulsive self-interaction, so that we can make the Thomas Fermi approximation, which amounts to neglecting the quantum potential. In that case, the differential equation takes a simple form. It becomes linear, which is equivalent to the Lane-Emden equation for a polytrope n equal 1. And then in that case, it can be solved analytically, leading to this profile represented here. So in that case, the density vanishes at some finite radius. And this radius is independent of the mass of the system, which is a property of n equal 1 polytropes. And it is fixed entirely by the ratio between the scattering length and the cube power of the mass of the boson by this relation here. And when we take into account repulsive self-interaction, we can describe ultra-compact galactic halos with a much larger mass than before. Now the mass of the boson can go from 10 to the power minus 22 up to 10 to the power minus 3 electron volt. Now, if we consider the general case, we can solve this differential equation numerically, and we can obtain the mass-radius relationship. So we have to distinguish two cases, the case of a repulsive self-interaction or the case of an attractive self-interaction. So if the self-interaction is repulsive, the mass-radius relationship is monotonic, and the radius increases as the mass decreases. So in the limit of small mass and large radii, we are in the non-interacting limit that I showed here previously. And when we increase the mass of the system, the radius tends to a constant value given by this expression showed before, and we are in the Thomas Fermi limit. And here we have an equilibrium state for any value of the mass. Now, if we consider attractive self-interaction, which is the case for QCD axions and ultralight axions, in that case, there is a maximum mass, which results from the competition between the attractive self-interaction, the attractive gravity, and the repulsion due to the quantum potential. So if we are below this maximum mass, there are two equilibrium states, but only one is stable, the one with the largest radius. The other one is unstable. And if we are above the maximum mass, there is no equilibrium state anymore, and the system will collapse. So below the maximum mass, we have stable equilibrium states, which are called dilute axion stars. And above the maximum mass, there is no equilibrium state anymore. And typically, we have two possibilities. We can have dense action stars if we take into account higher order repulsive self-interactions in the potential, or we can have a Bose-nova with an implosion and an explosion with the emission of relativistic axions if we take into account special relativity into the problem. We can also obtain the mass-radius relationship analytically by using a variational principle and the Gaussian ansatz for the wave function. So quite generally, it can be shown that the energy, that a stable equilibrium state is a minimum of energy at fixed mass. So the energy of the self-gravitating Beck is given by this expression. This is the sum of the quantum kinetic energy, the self-interaction energy, and the gravitational energy. And if we make a Gaussian ansatz for the wave function, we can transform this functional into just a function of the radius r for a fixed mass m. And if we minimize this function, if we minimize the energy with respect to r at fixed mass, we obtain the following expression of the mass-radius relationship, which is in relatively good agreement with the numerical results that I showed previously. In particular, it is able to give a good approximation of the exact maximum mass shown here. So now let us consider general relativistic Bose-Einstein condensates at 0 temperature. So we consider the possibility that because of their superfluid properties, some compact astrophysical objects, like neutron stars, for example, may contain a significant part of their matter in the form of Bose-Einstein condensates. So for example, the neutrons in the core of neutron stars could form Cooper pairs of mass 2 times the neutron mass and behave as bosons. So in that case, the neutron star, which is usually a fermion star, would be a general relativistic boson star or Beck stars. Furthermore, it can be shown that in the Thomas Fermi approximation, a self-gravitating Beck is equivalent, a relativistic self-gravitating Beck is equivalent to a fluid described by this equation of state. And consequently, the equations of the problem become the Tolman-Oppenheimer-Volkoff equations, which express the condition of hydrostatic balance in general relativity, coupled to this equation of state. So we can solve this equation and plot the mass-radius relationship. So for small values of the mass, we are in the Newtonian regime, and we recover for small mass the constant radius that I showed previously here. And when we increase the mass of the star, relativistic effects come into play, and there is a maximum mass above which there is no equilibrium state, and the system collapses towards the black hole. We can also show that the series of equilibria becomes unstable at this maximum mass, at the turning point of mass, and that a new mode of instability is lost at each subsequent turning point of mass. So the maximum mass of Beck stars in the model that I showed previously is given by this expression, and it depends on the scattering length of the bosons. And this is potentially interesting for the following reason. If we model neutron stars as an ideal fermion star, like in the model of Oppenheimer and Volkoff, the maximum mass of neutron stars would be fixed to this value, 0.7 solar masses, which is smaller or of the order of 1 solar mass. But if the neutron stars is a Beck stars, its maximum mass is given by a different expression, which depends on the scattering length. And by choosing appropriately the parameters, we can get a maximum mass in the Beck model of the order of 2 solar masses, which could explain the observed neutron stars with masses in the range of 2 to 2.4 solar masses that cannot be explained with the Oppenheimer-Volkoff ideal fermion star model. So finally, I will consider the case of dark matter halos made of Bose-Einstein condensates. So we can show that large dark matter halos have a core envelope structure with a quantum core, which corresponds to the big stars that I showed previously, surrounded by an approximately isothermal envelope. And the question is to determine the core mass as a function of the halo mass. And to that purpose, we can use a maximum entropy principle to look for the most probable state. So we can compute the entropy of the system as a function of the core mass and maximize the entropy with respect to the core mass at fixed total mass and total energy to obtain the most probable core mass of the system. So if we do that, we find that the maximum entropy principle is equivalent to the velocity dispersion tracing relation, saying that the velocity dispersion in the core is of the same order as the velocity dispersion in the halo, which can be written like that, where mc is the core mass, rc is the core radius, mh is the halo mass, and rh is the halo radius. Now we have the following relation between the core mass and the core radius. So this is the relation that the mass radius relation that I showed previously here, and which can be obtained from an analytical model. So we have this simple mass radius relationship. We also have the following relation between the halo mass and the halo radius, where sigma is the universal surface density of dark matter halos inferred from the observations. So now if we substitute these two relations into the velocity dispersion tracing relation, which is equivalent to the maximum entropy state, we obtain the following relation between the core mass and the halo mass for any value of the mass of the boson and the scattering length, positive or negative. So in the non-interacting case where AS is equal to 0, it reduces to a pure power law like that. And in the opposite case where we have a strong repulsive self-interaction, so that AS is large, it reduces to another power law like that. So we can plot the core mass as a function of the halo mass. So for non-interacting boson, we have this power law, as I said before. In the Thomas Fermi regime, we have this power law, and in between, for positive or repulsive self-interaction, we have these different curves. So in that case, the mass increases monotonically with the halo mass. The case of attractive self-interaction is potentially more interesting because you can see that now the core mass increases until it reaches a critical point corresponding to the maximum mass that I showed before, obtained here, at which the core becomes unstable and collapses, forming a Bose-nova or a dense action star. So in sufficiently large halo, the core mass can reach the critical mass and collapse. So this would lead to the possibility that in this Bose-Einstein condensate model with attractive self-interaction, large dark matter halos may have a collapsing core forming a Bose-nova or a dense core. But if we use the parameter, so of course they are not well known, but if we use the values of the parameter of the boson mass and self-interaction that are expected, unfortunately, we find that the largest halo have a mass smaller than this critical mass. So apparently this collapse may not occur. But as I said, the values of the parameters are not strictly obtained for the moment, so this possibility remains possible. So I will stop here and give a list of references on this work. Thank you for your attention.
Thank you so much, Pierre-Henry, and thank you for being exactly on time. We have actually 4 minutes up to the end of this session, and we have time for a couple of questions. Dawood has a question, but I have to inform that after the 5 minutes, this session will be closed. So I would like to thank everyone to participate in this session, and let Dawood ask his question. Dawood, please go ahead.
Hi, and thanks a lot for your nice presentation. My question is related to the first part of your presentation that you define a equation of a state based on the Graf-Pytowski equation. Could you please explain for me that the dilute limit that you will consider for this equation of a state, and also the relation between this equation of a state, which is also a Bose-Einstein condensation, and the equation of a state that you define in your second part of your presentation, which then you solve based on Tolman-Oppenheimer-Volkoff equation?
Okay, so the first part of the talk is based on the non-relativistic limit of the Bose-Einstein condensate. So in this, so I am using Newtonian gravity and non-relativistic kinematics. And indeed, I assume that the system is sufficiently dilute so that the Gross-Pytayevsky Poisson applies. So this is indeed an assumption of the work. But if we agree with that, so the equations of the problem will be the well-known Gross-Pytayevsky equation. And if we make this transformation, the Madlung transformation, introducing a density given as usual by the square of the wave function and the velocity field related to the phase of the wave function, we can transform, and this is exact at that level, we can transform the Gross-Pytayevsky equation into fluid equations. And in that case, the pressure P here is related to the cubic term here, and it is exactly given by this expression. So if you assume the Gross-Pytayevsky equation, the equation of state of the system is exactly given by that. And in the second part of the work, I'm considering a relativistic Bose-Einstein condensates. So in that case, the derivation of the equation of state is more complicated. I have not given it in this talk. And it is valid only in the Thomas Fermi approximation. But again, if we consider a scalar field described by the Klein-Gordon-Einstein equations this time, with a phi4 repulsive self-interaction. And if we are in the Thomas Fermi approximation, we can derive this equation of state and obtain this curve.
And my question is about that. You said that you have, in fact, we can say that we have two kinds of Bose-Einstein condensation: a non-relativistic Bose-Einstein condensation and relativistic Bose-Einstein condensation. Could you please explain for us the difference between these two?
I'm quite sorry. We have to switch off the session, but probably you can continue tomorrow if everybody agrees, right?
Yes.
Okay, as you want.
I think so.
Okay. Therefore, let's stop at this point. I'm really sorry, but we have sharp limits on the technical side.
Thank you.
Okay, thank you so much. Thank you to everyone for participating in this amazing session.
Thank you. Bye.
Bye, everyone.
Okay. I stay my email in chat. If anybody have questions, they can contact me.
Sure. Thank you so much.
So thank you. Bye.